Hi guys, and welcome back to my channel. This is episode number 4 of the water cycle and water insecurity revision series over here on my channel. Today we're going to be looking at the water balance and water regimes, so if that's what you're here for, stick around. Subscribe down below as I upload one of these every single week and you don't want to miss out. So let's just get into it. Water budgets. In the short term, water availability varies day to day, month to month and year to year. But over a longer period, there is usually a natural rhythm that balances out times of surplus with times of deficit. This balance is called the water budget and reflects the differences between inputs and outputs in any given area. A drainage basin provides the best geographical unit to observe and measure these rhythms, because factors within the basin control how much water is available at any given time. There are many components within a water budget, including natural and human factors that affect the hydrological process. Think precipitation, water diversion, groundwater surface flow, surface runoff, and then you've got your evapotranspiration, water diversion, groundwater flow out of an area, industrial or residential uses of an area. The budget can also be expressed as a water balance equation. It balances precipitation, surface runoff, river discharge, potential energy, and soil moisture and groundwater storage. Each year, whatever falls as precipitation should be balanced by the other components, written as the equation P equals Q plus E plus or minus S. These factors can also be shown on an annual budget graph. Rainfall effectiveness and water availability. Land use changes in river basin affect water availability and quantity. Potential evapotranspiration exceeds precipitation in the summer, leading to lower water levels in rivers, lakes and ponds. Soil moisture content also declines and vegetation may wilt. However, there is a delay between onset of dry weather and reduced soil moisture, as there is between rainfall and runoff. The UK's water year begins in October, when rainfall exceeds evaporation. Storage areas are recharged from that point and they're usually full by January. Overland flow increases until there is a water surplus, which then raises the flood risk. As temperature rises and rainfall decreases in spring, soils lose moisture and by late summer a deficit exists. Effective rainfall is the amount of precipitation remaining after evaporation. This means that places with similar annual rainfall can experience very different water issues. Parts of East Anglia in the UK, for example, receive similar annual rainfall to arid Arizona in the UK, but the rainfall effectiveness of both places is very different. Soil moisture in the hydrological cycle. The capacity of soil to retain moisture is vital to the hydrological cycle. The maximum capacity that soil can hold is known as its field or infiltration capacity. This is reduced when evapotranspiration exceeds precipitation, causing a water deficit. In South Essex, irrigation is needed for farming. Without it, a dry landscape would exist. Rainfall in Essex is spread fairly evenly throughout the year. Colorado in Arizona has short, separate bursts separated by periods of drought. Precipitation following a dry period is known as a recharge, when soil moisture levels increase. If soils saturate above field capacity, a water surplus occurs, generating surface runoff. Flash flooding is common in dry lands, where sun-baked soils cannot absorb intensive rainstorms fast enough. The surface soil becomes saturated, causing rapid surface runoff. Patterns of flow, regimes and hydrographs. So far it's clear that the amount of precipitation reaching a river depends on both local and drainage basin-wide factors, as well as climatic controls. The pattern of a river's flow or discharge throughout the year reflects all of these factors. The annual flow is known as a river's regime. At a local level, the effect of an individual storm can be shown on a storm hydrograph. River regimes. Tropical rivers generally have fairly uniform flow patterns, especially in areas where rain falls every month. However, worldwide, river regimes tend to have a seasonal pattern, whereby they respond directly to the amount of precipitation. There are two main types of river regimes. Simple regimes. These are where the river experiences a period of seasonally high discharge followed by a low discharge. They are typical of rivers where inputs depend on glacial meltwater or seasonal storms such as monsoons. Rivers with temperate climates, which rise in mountainous regions where summer snowmelt occurs, tend to be like this. And then you've got your complex regimes, where larger rivers cross several different relief and climatic zones, and therefore experience the effect of different seasonal climatic events. This is true for rivers like the Mississippi or the Ganges. Human factors can also contribute to their complexity, such as damming rivers for energy or irrigation. A river's regime reflects differences in precipitation, temperature, evapotranspiration, or land use throughout the river's catchment during the year. Characteristics of the drainage basin itself, so shape, geology, soil type, and cover, as well as human intervention, influence a river's regime. Some of the world's longest rivers are several thousand kilometres in length, so they may cross several different climatic zones and encounter very different land uses, population densities along their length. The longer the river, the more complex the variables seem to be, making the river regime more complex. Storm hydrographs. A hydrograph is a graph showing the discharge of a river at any given point in time. A storm hydrograph shows how a river responds to a particular storm and displays both rainfall and discharge. When rain starts to fall, only a fraction of it will fall directly into the actual river channel, so the discharge does not increase immediately. Most rain falls onto the valley sides and takes time to get to the river. As the water makes its way to the river, the discharge increases, shown as a rising limb on the graph. The gap between the maximum rainfall and the peak discharge is known as the lag time. Players in the hydrological cycle. Planners. Within the UK, planners are required to determine whether any proposed development, such as a new housing estate or industrial use, will influence flood risk within the change of land use. Within England, the National Planning Policy Framework sets out strict guidelines. Decisions vary on how much weight is given to environmental factors, which maintain river flow unaltered, versus those favouring economic development, which alter river flow. Economic development increases the likelihood of a higher flow and a higher response time. Developers have to show that land use changes will not increase runoff beyond that estimated for a greenfield site. SUDS systems. Recently, sustainable drainage systems, SUDS systems, have been introduced to reduce surface runoff produced by rainfall. Examples of these include green roofs, on which vegetation cover planted over a roof a waterproof membrane, infiltration basins, shallow depressions dug out to delay surface runoff and increase infiltration, permeable pavements to delay runoff by using gaps in between pavement slabs, rainwater harvesting, collecting water from roofs to be recycled for irrigating gardens, for example, soak away, a channel dug out to disperse water into the ground, filter drains, trenches filled with gravel to take runoff away, detention basins to delay storm runoff for a few hours, and wetlands, retention areas with marsh or wetland vegetation. And that is the end of this episode. I hope you learned something. Please do subscribe down below so that you don't miss the next episode, and I will see you same time, same place next week, Monday, 4:30 p.m. Bye guys.